Good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. And today, by accident, is the International Day of Light. Yeah, that every year on the 16th of May. Yeah, every day is Day of Light. Yeah, but today is the special International Day of Light. And in order to celebrate it and raise a little bit of awareness for everything that is connected to light and photonics and so on and so forth, we invited Professor Andrew Forbes from the University of the WITS to give us a colloquium. Yeah. So, and Andrew, as I said, is a distinguished professor at the WITS School of Physics, and he's leading the laboratory for structured light. Yeah, so it's really appropriate and on topic. Yeah, Andrew is probably known very well in the physics community and also outside of it. Just to mention a few things, he's a founding member of the Photonics Initiative of South Africa. He was involved from the very beginning with South Africa's quantum technology roadmap. He's a fellow of SPI, of OSA, of SIP. He's a member of the Academy of Sciences. He's A-rated. He's the editor-in-chief of Journal of Optics. Yeah. And he won numerous awards, including, I don't know, just a random one, the SIP gold medal, which is probably the highest medal for physicists in the country. Yeah, and Andrew has, I think, spent his whole career working on classical and more recently also quantum light. So, Andrew, we are very happy that you're with us today, and we are really looking forward to your presentation. Before I ask you to start, sorry, I always forget to tell the participants, or to remind the participants, to use the Q&A facility to ask questions. And maybe at the end of the talk, if you raise your hand, if we have the time, we can give the participants the right to speak and ask the question in person. Sorry, this was my Teams ringing. So Andrew, please, you're welcome you're already sharing your slides. You're welcome to start your presentation. Thank you very much.
Francesco, thank you very much for the kind introduction and for the invite to speak this afternoon. It's a wonderful seminar colloquial series that you run, and I'm delighted to be part of it. So as Francesco explained, today is the International Day of Light. Actually stems from the International Year of Light in 2015. It was arguably the most successful of all the UNESCO international years, so it's been said. And that's why they decided to continue on an annual basis with the 16th of May as the International Day of Light. And because we're here with a lot of theoreticians, I decided to be a little bit sort of controversial and not speak about our quantum work, which is traditional quantum optics, but to look at quantum-like classical light. And that seems to be a contradiction in terms, but hopefully I convince you that there's some merit to that by the end of it. It's not a technical talk. Hopefully there's something in it for everyone, and I'm quite happy to address questions at the very end. So as Francesco said, I'm from WITS University. I run a group in structured light. Actually, this year we're celebrating our centenary, 100 years old. And if you come a little bit to the left of this great hall, you find the School of Physics. It sits over here, just behind these trees. I believe it's the largest physics school in the country. And inside the School of Physics is my lab, and we play with structured light. And by that, we mean controlling light in all its degrees of freedom by a variety of approaches. And here would be a typical photograph of our lab to show you that really at the center of everything we do is light. So what do I mean by structured light and controlling all of light's degrees of freedom? Well, what I mean is, of course, we know that there are degrees of freedom to control in light. Our textbook version, of course, introduces a very early stage, the familiar terms of amplitude, phase, polarization, for example, a wavelength and a frequency, etc., etc. But there are many other degrees of freedom that can be subdivided, perhaps some of them not so obvious. Certainly in the quantum world, things like path would be a well-known controllable degree of freedom of light. But there are others that are less so obvious. And what we try to do in structured light is to identify what are the degrees of freedom, how could we control them, And having controlled them, how could we harness that light for a range of applications, classical and quantum? If you'd like to know more about that topic, go and have a look at this nice review article that we put out a couple of years ago. It summarizes everything we understand about the topic. So to create structured lights, we typically have a range of devices in our laboratory. And I'll just give you one example on this slide because this is not a structured light talk. Here would be a little MEMS device. It's the type of technology you get out of data projectors. If you take an old data projector and pull it apart, you find these little micro mirrors that can switch on and off. So this is an amplitude controlling device. But even with very simple functionality, we can create very exotic structured light. So here you see an experimental video of the intensity pattern being structured. And we can do the same thing with other degrees of freedom as well. So simple devices to control light's degrees of freedom. Probably the most popular pattern that we would create in our lab would be light that carries orbital angular momentum. So I have a standard 1 or 2 slide tutorial on this. If you've heard it before, then bear with me. And if you haven't, then hopefully you learned something interesting. So here would be, again, our textbook blob of lights. It would be, if I was giving this talk live, it would be what you might see from a laser pointer if you put it onto a camera with a false color representation of how much light there is. So lots of light in the middle, falling off as a Gaussian function towards the edges. Now, this blob of light doesn't carry any orbital angular momentum. So we give it an L index of 0. And it has planar wavefronts near the waist. If the light diverges out, of course, it gets a bit of curvature, but near the waist, it's planar. And now what I'm going to do is I'm going to twist these wavefronts and give them 1 twist per unit wavelength. So if I do that, I'll get this helical shape coming out, or more a spiral, in fact. It now carries 1 h-bar per photon of orbital angular momentum. And this is in the z direction. It is a donut beam, and it has an intensity null. So there's no light in the middle because the phase is undefined. And instead of twisting it once per unit wavelength, I could, of course, twist it twice. Now I get a helical structure. It carries 2 h-bar per photon. You might have noticed that the ring got a little bit larger in its diameter. The null is also a little bit bigger. And of course, I can keep doing this in principle all the way to infinity. In practice, in our lab, around about 600 is the maximum that you could get to with typical devices. Okay, so I've been twisting it in a particular direction. Of course, I can twist it in the opposite direction. So instead of going clockwise with my twisting, I can go anti-clockwise. And so instead of 1 h-bar per photon, I can go minus 1 h-bar per photon. And again, in principle, all the way to minus infinity. So you see you have a very large discrete alphabet in which to probe both classical and quantum physics. And now what we're going to do is we're going to take these twisted lights. I'll illustrate it with 2 opposite helicity states, so -1 and +1, but in principle, it can be anything. And I'm going to give them 2 different polarizations. So one of them could be left-handed and the other one could be right-handed. So, and that I'm referring to the circular polarization states. So what does this mean then? What would the new state look like? Well, let's unpack the 2 components. So on the polarization states, we have a left component and a right component in the beam. Of course, we can represent just the polarization on a Poincare sphere, where the poles would be left and right spin states. So this would be describing the spin angular momentum of light. But I can also construct an equivalent abstract sphere, the block sphere, where the spatial modes sit on the 2 poles. So for example, an L mode of OAM and a minus L mode, perhaps +1 and -1 of orbital angular momentum. And what would the equator be? The equator would, just like the polarization case, be the superpositions of these 2, which happen to be the Hermite-Gaussian modes in the case of the + and -1 states. So on the left, we have a sphere that describes the spin angular momentum. And on the right, we have a sphere that describes the orbital angular momentum. And the vectorial state that I showed you in the previous slide is then a vectorial or tensor product of these 2 spaces. So now it describes the total angular momentum of the light. So on the pole, I would have each of the 2 scalar states. a particular orbital state and a particular spin state, maybe -1 on the north pole that's left circularly polarized, and +1 on the bottom pole that's right circularly polarized. And what would the equator be? Again, the superposition of these two states. So these would be vectorial states of light. And if you look at them and you go to your lab with your favorite device, you can actually create these states of light. Here you see a donut beam being exposed out into the distance. And in principle, it could hold these vectorial and scalar orbital angular momentum states. And I'm going to use them in the rest of this talk to describe what I mean by quantum-like light. So let me unpack the vectorial nature a little bit more. So if you teach optics like I do at WITS, then you would be familiar with Jones matrices or Jones vector. And what we can do is describe the electric field in terms of its two transverse components, maybe an X component and a Y component. And usually we imagine that the spatial part of the field and the polarization part can be separated in their treatments. So here I'm going to show you a cartoon of a Jones vector. And in it, I'm only going to have a spatial component in the horizontal part of the light, or in the bottom example, only in the vertical part of the light. And so as a consequence, the beam at the top is, of course, horizontally polarized, and the beam at the bottom is vertically polarized. I could, of course, put the pattern into both components, either with no phase difference as in the top, or with a phase difference as I show in the bottom. And that, of course, would change the polarization, in this instance, to be diagonal or circular. But what you see is that in all the examples I've shown you so far, you could have factored out this pattern of light to write the pattern and the vector separately. But what if I create beams where the two patterns are different? So I have an X component and a Y component that are not the same. They could be orthogonal, in which case I cannot factor anything common out. What happens then? Well, then the polarization state must change across the field because the amplitude and phases change everywhere. And so I have an inhomogeneous polarization structure. And depending on what the components are, how they look and what their phases are, I could get all sorts of exotic polarization states. And the consequence of this is that if I pass such a beam through a polarizer, traditionally we would expect that the intensity would oscillate, following Maulis's law. But in the case of the vectorial beam, what happens is that the pattern of light changes. Your spatial projection alters according to your choice of polarization measurements. So a measurement on one degree of freedom affects the outcome of the other. And that's the kind of language that we very often hear in the quantum world. A measurement on one particle affects the outcome of another. And so if I write my vectorial beam in a quantum-like notation, and here I've done that on the left, you can see the similarity to an entangled state. So are they equivalent? Well, of course not. On the right, this would be, for example, a real entangled state with non-local correlations. And here I have a classical beam. But there are certain things that they hold in common. One of them is non-separability of the states. The difference, of course, is that here I have degree of freedom 1 and degree of freedom 2. It's one single beam, or you can think of it as one photon if you like, but two different degrees of freedom. On the right-hand side, I typically in an entanglement experiment, at least in my lab, would be two different particles, but 1 degree of freedom. So this would be the orbital angular momentum of particle number 1, and this would be orbital angular momentum of particle number 2, written as a superposition in a particular basis. And what this implies is that perhaps from the similarity, I can start to think about a notion of classical entanglement based on this idea that classical light is non-separable. In fact, the idea of non-separability is certainly not unique to quantum mechanics. It's very common in the physical world. It's very rare to find something that's completely separable. The weather map is a non-separable entity. If you were to factorize out a common temperature, your geographical map of the country, of course, would alter. Okay, given not the equivalence, but the similarity, could we exploit it to benefit the classical and the quantum world by constructing quantum-like light? And the first thing we can do is take some quantum tools across to the classical world. So here you see a visualization of a density matrix, something very common in the quantum world? And could you construct a density matrix for your classical vectorial beam? Of course you can, and the idea in the classical world would be that on the left part of the spectrum would be a purely scalar beam that's completely separable, all the way through to a purely vectorial beam that is completely non-separable. And because we have a two-dimensional system here, we can use things like the concurrence, very common measure of entanglement for qubits, to measure the non-separability or the degree of vectorness of a classical beam. And so just like you would do a quantum measurement, I could take my classical beam, so here it is on the top left corner, and do two projective measurements. Rather than measurements on two different particles, it will be two measurements on the same beam. One will be the polarization degree of freedom, so measure the different polarization states, and then based on the outcome, measure the different orbital angular momentum projections. I'm using orbital angular momentum as my example throughout this talk, but you can replace the patterns up here with whatever your desired basis is. So we've done exactly this. In fact, we've done it many times in our lab, but the example I'll show you here is something we constructed for educational purposes. And the idea is to build a simple quantum simulator that allows the students to do state preparation and state measurements with an all-automated home-built system that allows you to 3D print all the components and run an experiment as if you were doing a real quantum experiment. So in this little tutorial article that we show up here, we give you all the code and the drawings to print everything that you need to make. And here's a little video. We had some visiting students who did this in our lab from Harvard and Glasgow. And the little video talks you through the process. I'll only show a couple of minutes of it. The full video is online as part of the tutorial article. But what you see is that it's all home-built components. We're doing projective measurements in a spatial basis, as well as polarization. The measurement is on in principle, could be a photodetector, but here we're just using a camera. You measure the intensity only at one spot, and you get the outcome of the projection. And you keep doing this, and if you run it long enough, you can start to construct the outcome of your projections. So on the left, you see the outcome of a scalar state. So this would just be an orbital angular momentum beam that's left circularly polarized. And you see, not surprisingly, the outcomes of all the right states are 0. And on the right here, you see a vectorial beam. So it looks like our non-separable state. And of course, the outcomes look rather different to the scalar state. In the quantum world, this would be no entanglement, and this would be maximally entangled. And so from these projective outcomes, you can, of course, construct a density matrix that is consistent with these measurements. And if you do that, this is what you find. So here you have a density matrix that shows no entanglement. And here you have a density matrix that's representative of a typical Bell state, a maximally entangled state. And just to convince you that this works, in fact, you can do, of course, also a Bell measurement. So you can show a violation of a Bell inequality. Again, on the left is the scalar beam. And on the right is the characteristic 0 to a half oscillation, as you would expect as you do a conditional measurement. Having measured 1 degree of freedom here, you rotate your measurements on the other degree of freedom. And you can show by calculation from these data points and the fitted curves that indeed you violate a Bell inequality by several standard deviations. And perhaps the real proof in the pudding of all of this is to ask a question, well, just how close to quantum is it really? This experiment with 3D printed parts and using bright classical light, how far does it deviate? And so to show you that, on the left, at the top and the bottom, I have the outcome of a real quantum experiment. This was 2 entangled photons created in our lab. They were expressed in the orbital angular momentum basis. So this is the orbital angular momentum of photon A and of photon B. You see we have many dimensions. It follows an anti-diagonal because orbital angular momentum was conserved and it had to add up to 0 in this case. And here are the projective measurement outcomes. And on the right-hand side, I have the classical experiments. So now it's the created orbital angular momentum and the measured, because it's the same beam. And here you see it's 2 different degrees of freedom rather than 2 different photons. but just a visual comparison reveals the similarity. And of course, you can quantify that with real numbers and show that, in fact, nature, in terms of the simulation, can't tell the difference. And this equivalence, at least at some level, can be exploited to enhance the quantum world. So to show you that, have a look at this cartoon example that we ran a few years back. So at the top level of the cartoon, we have Alice creating two real entangled photons. She keeps one of them in her lab, photon B, and she sends photon A across some channel. In this case, it's atmospheric turbulence, so it's a noisy channel. And on the other side, Bob receives the photon. And now what happens? Well, the initial entangled state, of course, gets perturbed because photon A, of course, it's an orbital angular momentum, it's a pattern of lights, and patterns of light get distorted in the atmosphere. If you ever looked across the bay and you've seen the twinkling of the lights, well, then you know that light gets distorted in the atmosphere. So the entanglement will change. At the bottom is a classical equivalent of that situation. This time, Alice prepares a vectorial beam, so not two different photons, but one beam in two different degrees of freedom. And she constructs the beam so that one of the degrees of freedom, in this case, degree of freedom B, is polarized. It's a polarization degree of freedom. That, of course, is not affected by the atmosphere. The atmosphere is not birefringent, so the polarization state doesn't change. And so when she passes the beam through the atmosphere, of course, degree of freedom B, the polarization, doesn't alter, but degree of freedom A does. And so it seems that these two cases should yield the same decay in the vectorness of this beam and the entanglement of the true entangled photon case. And that's what happens. I showed only up here at the top corner because it's quite an old result now, but the classical and quantum data is shown in the red and the blue, and you can see that they both sit on top of the theoretical curve, which is the green, and essentially the message is that nature can't tell the difference, in this case, in the way it behaves on the decay of entanglements between a true entangled state and the classical beam, which means that you can use the classical beam to unravel what the channel is doing, because you can make as many measurements as you like on the bright classical beam, which is not the case for, of course, the quantum states. And so that's what we show at the bottom, that because we can make as many measurements as we like, we can find out exactly what is wrong with the states, we can correct it, and so we can take the fidelity, which would have decreased quite rapidly as we made the noise larger, and its noise goes larger to the left in this plot. We can recover almost perfect fidelity by this procedure. So this is classical light enhancing a quantum process, but it's quantum-like classical light. What about actually doing some quantum mechanics with classical light, not just mimicking it, but really doing it? So what you can do is pick up your quantum mechanics textbook and page through it and ask yourself, okay, which protocols or processes need the superposition principle or exploit non-separability? So let's say you come to quantum communication and you see, oh no, it needs single photons, it's based on no cloning and no copies. So no, you can't do that with the classical light. It would not be secure. But if you come to things like the Grover algorithm, which is a computational algorithm, you find that you only need the idea of superpositions. And the idea of superpositions is not unique to quantum mechanics. It occurs in all wave theories. And so you should be able to do things like the Grover algorithm with classical light. And indeed you can. So on the left here, I show a little summary of how this works. Actually, this little cartoon was made by Thomas Conrad. I think it's a lovely way to explain it. And the idea goes like this. You have a database, and in this database, you have something that's been marked that you would like to find. And your initial state vector might be this vector over here. And essentially is saying that your drop-down component to all the states you don't want is quite large, and the component in the state you're looking for is quite small. And what you'd want to do is move the arrow up towards the vertical so that you have a higher probability of being or finding this the state that you desire. And the way Grover works, if you want to think about it geometrically, is that it first does an inversion around all the unwanted states. So it rotates the vector from here to the bottom. And then it does another inversion about the original point. So it does a reflection through this point back up to the top. So first about the unwanted states and then about the original states. And you see with just one step, the vertical component of the new state is of course much higher than the original. And so your probability of finding the desired marked entry is much higher. And we've done exactly this in a classical experiment. And the results on the right show you the outcome of one iteration. So that's the power of Grover's algorithm. It takes very, very few iterations for the marked state to emerge from an equally distributed, normally distributed sequence where its probability is equal to all the others. So here you see the marked states originally were 3, 9, and 11. And if you just glance at the probabilities after one round trip, they were all equal to begin. You see indeed that 3, 9, and 11 are now significantly higher than all the background states. And what sort of classical experiment does it take to perform this? How complicated might it be? Is it harder, for example, than the quantum experiments? No. In fact, it's just a telescope. It turns out that the way Grover works is exactly the same as how Zwicky phase contrast microscopy works. You simply have to mark a state with a phase, have a telescope, and voila, after one iteration through the system, your initially evenly distributed kind of marked state appears as a distinct peak. And of course, what you can do is take your telescope and put it inside a resonator that we depict here by two mirrors, this grayish mirror on the left and the same on the right. And now you can imagine that the light might bounce back and forward many, many times. So many steps through the system. And this, of course, would rapidly increase the weighting of the desired state. I'm going to return to that in just 2 slides from now. What else could you do with classical light that only uses superpositions? Well, similar to this idea, you could do a quantum walk. The idea behind the quantum walk is that the walker takes all paths simultaneously. You have a superposition of all the paths, and it's the interference of all these paths that then give you the outcome. In a classical walk, it's one path at a time, and so you get one outcome. And of course, in a classical walk, you would, if your walker position starts at 0, you would typically end up with a sort of normal distribution, Gaussian distribution, where most of your little balls or walkers end up near where they started, and then to find yourself far away from the initial position is quite hard. In the quantum walk, it turns out that because of the interference, you can sample very far away from your initial position after far fewer steps. So quantum walks are very popular for trying to sample large databases. So how could you do this classically? Well, in fact, all you need to do is construct a vectorial beam where you hold the superpositions in the 2 different polarization states. The polarization allows you to do some degree of a coin flip with appropriate optics. The superposition allows you to hold information about where the walker is, allowing the walker to take all the paths simultaneously. And then hopefully you can get the quantum-like signal, which would be these peaks on the edges rather than a peak in the middle. And because you want many, many walks, so unlike the Grover, which had only one iteration without the mirrors, now you put it into a loop, so like a resonator, and that's what's depicted here in the red. So the light is going round and round and round, and after every trip, it's doing these operations. So every round trip is simulating another step of this walker. And then you look at the output of this after each round trip. So you need a bit of timing optics when you do this with light, and you direct the output to some detectors to determine where is the walker and what does the distribution look like. And all of this you see is done with a pulsed laser. So this is bright light. So this is a schematic, very pretty schematic made by Berenice on how the quantum walk could be implemented in the lab. And to show you that it really works, So here you see some outcomes, experimental and theoretical. The theory of the blue curves, blue bars, sorry, and the experiment of the little black pins. And you see that they agree very, very well. And if you look at it, then after a certain number of walks, you find that the peaks are indeed on the edges and not centered around the middle. And the little dash curve shows you what would happen if this was a classical walk. And you can see very clearly that it agrees with the quantum theory. Of course, you can change the symmetry of the walk from symmetric to asymmetric, and you can change the nature of the coins from, in this case, the identity coin or a not coin, and many other variations. So lots of different flavors of quantum walks can be done in this type of system. And of course, all we're doing here is looping the light around repeatedly many times and watching it as it comes out. So this is an example of classical light really doing something that we would have thought was purely quantum. But I want to use this example to launch into something that we've been doing recently, which is to say, you know, one thing you cannot do in the quantum world is clone the states. So amplification is not allowed, but there's nothing prohibiting that being done in the classical world. So if I were to take my resonator, shown here with two mirrors, the mirror at the front and the mirror at the back, similar to what I showed you with the Grover case, why don't I just put some gain in the middle? What if I have a resonator with some gain? Of course, we all know what that is. That's a laser. So could I have a laser that does these processes for me and generates these quantum-like states of light? So in the context of our research, we would put this under structured light directly from the source. So structured light lasers. So the first time we created this quantum-like light from a laser was using geometric phase. I don't want to go into all the details about that. If you're very interested, you can ask me some questions at the end. But this is what the laser looks like. It's a textbook laser, except that it has some geometric phase elements inside it. And geometric phase allows you to map spin to orbital by a spin-orbit coupling process. And here you see nice scalar orbital angular momentum beams coming out, but they're not quantum-like. And so I return to this higher order Poincare sphere that I showed you earlier. And here you see that these are experimental images, I can move anywhere around the sphere. And I can generate all the beams that I want, from scalar on the poles to vectorial on the equator. And to confirm they're vectorial, I can do exactly what I showed you earlier. I can actually measure what the profile looks like after a polarizer, or I can do this vectorness measurement to quantify it with a more precise number. And in this particular example, you can show that it's a very, very pure radially polarized light. In fact, we can break the symmetry of this process. So remember, all the states I showed you had plus L and minus L. And for example, this case is +1 and -1. But I can have arbitrary patterns at the north and south poles, and I can have arbitrary orbital angular momentum. And so actually quite recently, we've shown that you could put a metasurface inside the laser and generate superchiral light with asymmetric states. So in other words, in the context of this talk, what it means is that you can take a modern optical toolkit and engineer this resonator, this laser, to give you any desired qubit state of quantum-like light. And you know, if you think about qubits, and for example, quantum computing, you don't just want one, you want many, and somehow you want them to be interacting and to control them. And so in our very latest work, in collaboration with a group in Italy, one of our former students went over there, and we've started to do some things with them. We've built this lovely laser. Actually, we did this in their lab. All the rest were done in our lab in collaboration with the CSIR. And what we've got now is a 10 by 10 array of these little metasurfaces. So this is 100 beams that come out of this laser, but they all interact. And the way we get them to interact is we take the metasurface and we simply displace it back a little bit, or rather the output couple, I should say, we displace out back a little bit so that these things interact by a Talbot effect. If you don't know what that is, you can ask me after the talk. But have a look at the structure of the resonator. That's all I want you to do. Do you see that it's Again, got a mirror at the front, a telescope made of 2 lenses, and a mirror at the back. It looks just like the Grover case. And so the question is, of course, could you search a database by carefully constructing the metasurfaces that mark one and not the others? And could you use this and the interaction that you get from the cavity for interesting dynamics? And the idea is that you kind of press a button, the laser does the computation for you, and the output light from the cavity is the answer to your problem. And just to show you, the output light from this particular cavity is in fact an array of light vortices, in fact, a crystal structure of vortices with optical Bragg peaks. So you can show that it's one coherent node and not simply an independent array of incoherent lasing apertures. So there's a lot of scope to take this forward. I'm going to end with one last example, and hopefully I can dispel the myth that you need very complicated modern nanostructured materials in order to do these types of lasers. In fact, you can make a quantum-like laser with nothing more than just the 2 mirrors. So here you see my cartoon again. I have a back mirror over here. I have a front output coupler, so some light will leak out of this laser from the right, and I have a gain medium, so it's a laser, but I have nothing else inside the cavity. And what I'm going to do is I'm going to make one of the mirrors curved and the other one flat, and then I'm just going to change the distance between them. So as you change the distance between the 2 mirrors, of course, what will happen is that there'll be certain distances where a ray could be very stable inside the system. Take, for example, this case, because I'm going to show it in a second. If the curvature and the distance is just right, then it's possible that a ray could follow a W-like trajectory. It could travel down to this mirror, bounce up, down, hit this return mirror just at the right normal incidence to come back on the same path. And this would be a stable path inside the cavity. Of course, we teach this in our undergraduate courses. We talk about light confinement in cavities as a prerequisite for a laser. You can also think of it as another way. This is a ray-wave duality laser. Often when we build our lasers, we support many, many modes and we get these blobs of light. So that is very much a wave version of how the laser works. But we can go all the way to the other extreme, which is a ray version of the laser. Here we have a degeneracy that if you can make this thing laze in this manner, what you would have is ray-like beams coming out, but they are one coherent mode. In fact, they're in SU2 states. This is the happy marriage between rays and waves. So we can do this conceptually, and here's our little cartoon illustration of what it might look like. So we have a laser at the bottom, and out are coming these rays or trajectories of light, which of course we can then mark and do things with. So if we take this example to illustrate the principle, it's this W-like states. We can build a laser that should, at least in theory, laze on that if you get all the parameters correct. And here I show you an experimental image looking inside the laser. So here is the back mirror, and here is the front mirror. And you see that we've measured the beam at different positions. And so the trajectory goes from the front mirror, bounces again, returns to the back and back to the front. And it's following this W trajectory that we expected. And so in fact, you can create that light. And then what can you do? Well, if you look at what comes out of this box, of course, this ray is following that direction. Here we have 2 rays coming out and 1 here. So we have 4 rays of light coming out. We can mark them with polarization. So that means that we have an 8-dimensional state. And we can play with that 8-dimensional state much in the same way that we would with a quantum state. We would path mark the states and control the paths. So I will not go into all the details, but here is an experimental setup that allows you to do that. So we can path mark the states. And what sort of states live in an 8-dimensional space? It's the GHZ states. So rather than a traditional polarization description of quantum GHZ states, here we have a classical version of an 8-dimensional GHZ state. And we can create all of them. And so here we show all 8 states with very high fidelity, around 90%. Every measurement is by its own density matrix, by a series of projections. And so in fact, we can create high-dimensional quantum-like light from the simplest possible lasers. And so to conclude then, I have 2 messages. One is, where are we going to go with this? Well, the idea is to go more into the lasers, but as lasers not for the output of lights per se, but the output that holds the answer to a computation. So use the laser as your solver to solve and search databases that would otherwise be very difficult. And with the aid of gain, of course, we can overcome the losses, so search very large spaces by applying quantum protocols inside such a device. I also think it's exciting to explore this boundary between classical and quantum states. The idea that in quantum mechanics, we have a single theory, and it's a wave theory. But in the classical world, we have a separate particle mechanics and a separate wave mechanics. But if we concentrate on the overlap, of course, we know that the paradoxical wave equation and the Schrodinger equation hold a lot of similarity. And I think we have kind of bypassed what that means, both from a physics perspective and from a teaching perspective. And so I believe that there's a lot of scope to take classical light into the teaching laboratories to aid our quantum experimentation, which typically in South Africa we don't do. And just to tell you, we're doing exactly this now at WITS. It was put on hold a little bit because of COVID, but we just got the budget to buy all the optics to do this. So hopefully we'll have quantum-like experiments to show the students how to run through all the protocols. So on that note, I think I need to come to the end. I always thank my collaborators on the topic of classical entanglement. We've done a lot of work with Thomas Conrad. So I must acknowledge all of his fantastic inputs on this topic. And of course, my students, but this photograph was pre-COVID, so it's a little bit old. In fact, I realized when I updated it and looked at where everybody was, that everybody almost in this photograph has moved on. So we really need to update our photograph with the newest version. But we run a small group at WITS, we play with lights, and hopefully today I've given you some indication of the excitement that light can bring and how it could maybe add a little bit of controversy, but also benefits in thinking about the overlap between quantum and classical physics in the perspective of photonics. And so I think with that note, I'm going to come to the end. So thank you very much for listening. I'm very happy to answer any questions you might have.
Yeah, thank you very much, Andrew, for a talk that was fantastic for the occasion. Thank you very much. It was very interesting. I think nobody so far added any question in the Q&A, which probably means that it was a very clear and understandable talk. But I see there are already a few raised hands. So let me allow a few people. Here is the first one was Zurab, and there is another gentleman, Lucas, who also has a question. So please, Zurab, you're welcome to unmute yourself and ask your question.
Hello, thank you very much for your talk. If you go back to the first part of your presentation where you were showing us different pictures of that donut picture and other pictures
Okay, sure.
of light projection. And then below each picture, there was a rotating diagram, the wave diagram. Yes, that kind of picture.
Right, yes.
For someone who is not very intelligent in physics, could you please explain what is the link between the bottom picture and the top picture? Does the bottom picture suggest how the top picture?
Good question. So the bottom picture, what I've done is I've taken the wavefronts. So the wavefronts are planes of...
Hello?
Hello, can you hear me?
Yes, we can hear you, Andrew.
I don't know why the person said hello to me then. Okay. So what we've done is we've taken planes of constant, the wavefronts are planes of constant phase. So I can twist the wavefronts. So in this case, for example, becomes a helical structure. And what does that mean? You can think of it like this. The pointing vector is normal to the wavefronts. So that means that the pointing vector is kind of spiraling. So that's what this means. I can also put a global phase, which might be, for example, a radius of curvature across it, but that just adds a layer of complexity. So the bottom is showing what the phase structure looks like. I like to think of more about a wavefront because phase in the context of vectorial light is a little bit complicated. And this is the intensity profile. So what does the intensity profile of such a beam look like? It turns out to be a ring of lights. And the reason is that the phase is varying everywhere around the beam. So in the center, it's not defined. Another way to think about it is that the twisting around the center is too fast. So the spatial frequencies are just too high, so you can't have any light. And so that's why you get an intensity null. So if you were to look on a camera, you'd see the picture at the top. And if you were to look in an interferometer, you would see these sort of like spirals in the intensity.
Thank you.
Thank you.
There is a question in the Q&A by Ismail. I don't know if, okay, let me read it because he didn't raise his hand. He says, great work demonstrating that superposition is a phenomenon present in many different physical systems. As you mentioned, there is no cloning. Is there also no equivalent of quantum wave collapse?
Yeah, that's a great question. So no, I would say not. I mean, we do have the conditional outcomes, as I showed in the little video that's, and maybe I can just go back to that. Yeah, so what we have, what is equivalent is this notion of the measurement on one degree of freedom affects the outcome of the other, similar to how you think about the wave function collapse based on the measurement of one affects the outcome of the other. This is the closest we get to, but this is all a local interaction in the same photon or the same bright beam. So in that sense, it kind of does and does not capture that essence. There's no, I want to be absolutely clear, the classical light is not quantum. It has some quantum-like properties that could or could not be exploited according to what you're trying to do. But yes, there's no substitute for entanglement if that's what you need for your process.
Yeah, thank you. Okay, I don't see any other raised hands or urgent questions in the Q&A. Let's give people maybe another 10 seconds to raise a hand if they want to ask something. Otherwise, Andrew, you know, after the colloquia, we usually have a brief kind of social event, social get-together on a platform called Kumo Space. If you can spare 10 minutes,
Sure.
I can invite people to join us there, and I will add the link in the chat as we speak. Sorry, I just. Here we go. Yeah, nobody raised their hand, so maybe we can meet again in a minute, just a time to get out of Zoom and into the other into the other platform to have a more informal chat, just a few minutes. Yeah. Okay, then Andrew, thank you very much. It was really great that we managed to celebrate the International Day of Light on the day.
Yes.
Thank you so much. That was just a lucky coincidence. Probably next year it won't be the case, but anyway, we'll make a plan for next year. Yeah. So thank you very much, and please, if you have a few minutes and you would like to engage with Andrew on a less formal setting, please join us in Kumo Space just now. So Andrew, thank you very much. I will see you on the other side just now.
Brilliant. Thank you very much again.
Bye. Bye-bye.
Cheers.
Bye-bye.